Hi friends, this is Mrs. Rona here, and I'm going to introduce you to our third type of circular motion that we're going to look at in this course, which is called conical circles or conical pendulums. So if you can, please take out your packets and you're going to follow along taking notes on worksheet 4. We're going to do number 1 together. And so this problem is a rubber stopper that is tied to a string is whirled around in a horizontal circle. So that's what you see as this picture over here. It is a horizontal circle, but we can also see there's some vertical components about this. There's an angle given. We're going to have to worry about some stuff there. And then we're given some information. So the problem says the rubber stopper has a mass of 15 grams. We want to convert that to kilograms. The radius of the circle is 50 centimeters. We want to convert that to meters. And it was moving at a constant speed of 4 meters per second. So as with everything in circular motion, we're going to start with a free body diagram. So if we draw a free body diagram for that stopper, I'm going to do it right below here. For free body diagrams in a circle, we want to show where that circle is. We're going to do a side view. And then I like to add in a centripetal axis so I can think about what is acting radially inward and what's acting radially outward. So force is acting on the ball. From the side view, we can see there is gravity, or sorry, not the ball, the stopper, pulling the ball down. And then the stopper is tied to a string. So we know strings exert tension forces, and it will exert a tension force along that string. So we have a tension force going up and to the left if the ball is over on the right. So that is your FT. We also see an angle given, so similar to unit 2, if we have a theta, if we have a force at an angle, we're going to split that into components. So I'm going to change colors for that, just so you know those are the components of the tension. But there's an FTX going to the left, and there's an FTY going vertically upward. Now, the stopper is going in a circle, so we know it's accelerating because its direction is changing. And so we have a force radially inward, that's that FTX, but it is not vertically accelerating. It's not accelerating up or down, it's just accelerating radially inward. So this force of gravity has to be equal to this FTY. Part A says what force causes the centripetal acceleration? The force that's causing centripetal acceleration is the force that's pointing radially inward. So it would be the FTX in this case. Part B says calculate the period. Period's time it takes to make a complete circle. So before I jump to B, I do want to write an F net C equation. So I'm going to add that here with my FTX. So I'm going to say F net centripetal is equal to that FTX. And we know we always set that equal to mv squared over r. All right, so that is our F net C equation, so we're good there. All right, so on to part B, calculate the period. When I look at our equations for this unit, we have an equation that is velocity of an object going in a circle is equal to the circumference divided by the period. So that would be the simplest equation to use to calculate period. Let me double check what variables I'm given. I am given the radius, so I could plug that in here. I'm also given the speed, the velocity. So cool, I can use this equation to calculate that period in the denominator. So I'm going to do that right over here. So the velocity is 4 meters per second equals 2 pi. I want to plug in the radius in meters, so 0.5 meters, divided by the period. And so I'm going to divide those two. Let me get my calculator out. I don't know where my calculator is right now. Hang on, friends. You get to come along on this journey with me. Calculator. Calculator. There's no calculator. I need to download it. All right, I'm not going to do that right now, but you guys can solve this equation to get a period. Period is going to equal something in seconds. So pause the video real quick, calculate that, and then compare with your neighbors so you make sure you have the right period. All right, now that you're back, let's do part C. Part C says calculate the angle the string makes with respect to the horizontal. So I need to find theta. And so I'm starting to think of some trig functions, right? Sine, cosine, tangent. And I would need to know the values of the forces on this triangle in order to solve for those. So if I'm looking for that, I would need to know FTX, I need to know FTY. FTX, I can use my F net equation that I did right here to solve for that. So let's do that first. FTX is equal to mv squared over r, because it's the radially inward force. So I know the mass, 15 grams divided by 1,000 is 0.015, times the velocity squared, 4 squared, divided by the radius, which is 0.5. So if I do all of that, again, I don't have a calculator, I'm not prepared, I'm gonna let you do the algebra for me. You're gonna get something in newtons as your FTX. But we're trying to find theta. So if I have FTX, going over to my triangle over here, I would also need to know either tension or FTY. Tension, I can't really think of a good way to solve that, but FTY, I could solve that if I know FG, because my F net Y is going to be tension in the Y direction minus the weight is equal to 0, because I'm not vertically accelerating. So FTY is equal to FG. And so I can do, back to our unit 2 equations, FG is mg to solve for that. So then I can take the mass, which is 0.015, times the gravitational field strength on Earth, which is 9.8, and I can solve for some amount of newtons. So grab your calculator and solve for FTY right there. So now that I know FTX and FTY, I can solve for the angle using a trig function. So I'm going to think through which trig function makes the most sense. If I have an opposite side and an adjacent side, I'm going to use tangent of theta. So tangent of theta is equal to, if I look at my triangle, the opposite side, FTY, divided by the adjacent side, FTX. So we have those numbers. You have FTX right here, so you're going to plug that in the denominator. You have FTY over here, you're going to plug that in the numerator. And for those of us that don't remember, how do I get theta by itself? Because I'm solving for theta, I have to do the inverse tangent. So the next algebraic step here is that theta is equal to the inverse tangent of FTY divided by FTX. So go ahead and grab your calculator. Make sure you're in degrees, because we want an angle in degrees, and solve for that theta and check in with your shoulder partner. All right, wonderful. Now the very last step is part D, calculate the tension in the string. So when they ask for tension in the string, their problem's not asking for FTX or FTY, they're asking for the hypotenuse. What is the tension? And so to finally solve for that, you could use a trig function, because you now know the angle, or I'm going to use Pythagorean theorem. So for part D, I'm going to say a squared plus b squared equals c squared. So I'm going to do FTY squared plus FTX squared is equal to FT squared. So you can plug in, again, your numbers from down below. This number in pink was our FTX. The number I highlighted in green was FTY, and you can solve algebraically for FT. So this is how we do conical pendulum problems, conical circles. The only new thing is this free body diagram, and I would argue it's not that new. We've done stuff like that in Unit 2. But with conical pendulums, FTX is the force that is causing centripetal acceleration. It's our F net C. And you're always going to find that FTY is balanced by FG in the vertical direction. All right, thanks for watching. Go ahead and try the rest of worksheet 4.